Hi, welcome to my trial lesson on Introduction to Organic Chemistry. If you are interested for my tuition classes, you can sign up via my email or my phone number. The soft copy for today's notes are in the description below. So let's go ahead with our lesson. Today we'll be talking about Introduction to Organic Chemistry. Before we go into detail, let's look at what is organic chemistry. Organic chemistry deals with mainly carbon, hydrogen, and other non-metallic elements. So for example, for molecules like carbon dioxide CO2 or carbon monoxide CO, they are not considered as organic, right? So although we mainly deal with carbon and hydrogen, other elements such as metals sometimes can also be found in organic reactions, right? So this is one reagent which you don't usually see, right? So it might look confusing to some students because you know that magnesium is a metal, bromine is a non-metal, and carbon is also a non-metal. You should have learned from your O levels that a metal and a non-metal usually form ionic bonding, right? Ionic bonds. So why for this case you have covalent bonds? Well, it all boils down to electronegativity. I will not go into detail. If you are interested to know why such compounds can be formed, please refer to my chemical bonding notes, right? So this is just a brief introduction about this part. Next, carbon can exist in various oxidation states and different forms. So here are some forms, which is the carbocation, carbonion, carbenes, and radicals. So let's just briefly talk about what are these species, right? So let's look at our example 1. Determine the charge on carbon, if any, for the following species as well as its oxidation state. Do the two terms mean the same thing? Well, what do you think? Do they mean the same thing? Well, if you look at the first molecule, you should be able to identify it as methane, right? So this is your methane. Now, how do we determine the oxidation state of, let's say, this carbon? Well, we usually talk about oxidation state when we deal with ionic species, for example, like sodium chloride. It's quite obvious, and by now you should be able to know that for sodium chloride, sodium has an oxidation state of +1, right? While for chloride, it is -1. Now, what's the basis of you saying this? Well, in order to get the oxidation state, we have to compare their electronegativity values. So by now, you should know that chlorine is more electronegative than sodium, right? And just a quick recap, this is your periodic table, right? And the electronegativity trend increases in this way as well as this way, right? You know that chlorine is somewhere here while sodium is somewhere here, which means that chlorine has a higher electronegativity than your sodium. So now, why elements with higher electronegativity tend to be negative? Well, you should recall that electronegativity is defined as the ability of the nuclei to attract electrons towards itself. So it makes sense to think that the higher the electronegativity, the more likely it's going to attract electrons, so the more negative it can get compared to a less electronegative element like sodium, right? So that is the basis of obtaining or deducing your electronegativity values, right? Now let's go back to methane, right? So for methane, we can do the same thing by assuming the methane adopting an ionic model. And recall from just now that in order to deal with it ionically, we have to look at the electronegativity. So for this, same thing, right? So now we compare the electronegativity value of H and C. And you should be able to know that C, right, has a higher electronegativity than your H. This means that if let's say I have an electron sorry, if let's say I have a bond between C and H, so this is C and H, right? C will polarize the electron cloud towards itself more, right? Although it is more, it's only slightly more because the electronegativity difference between these two is really small, right? Nevertheless, if we were to analyze it this way, we will know that carbon will attract electrons more towards itself, right? So instead of confusing yourself further, we can actually do it in a more simplified way, right? So I'll teach you this method now. So if let's say we have carbon and hydrogen sharing one bond, obviously, right? And we know that carbon is more electronegative than hydrogen, what we'll do is that we'll put a minus sign at carbon and a positive sign nearer to hydrogen. So we'll do the same thing for the rest, right? So you should have something like this. So what's next? After you reach this stage, what you have to do is you just have to, if you cannot see it, just circle the electrons or circle the charges which is on the carbon side. So for now, there's a total of 1, 2, 3, and 4 charges, and they are all negative, which means that your oxidation state for carbon is simply -4. And for hydrogen, since there's only one positive charge, it will be +1, +1, +1, and +1. So this is how you can obtain the oxidation state of the atoms in methane, right? So now, what about charge? Obviously, for this species, all the charges are balanced, so it has a net charge of 0. That is for methane, right? Now we can use the same method for this species. Right? So how do we find the oxygen states of all the elements here? Same thing, we can use the same method. So just like the previous scenario, carbon is more electronegative, so you'll get a negative charge. Now, what do we do with the lone pair? What do you think? Now, just imagine carbon has a valency of 4 electrons, right? Because it's obviously from group 4, right? So since carbon has 4 electrons, we count it here. It actually has 5, so the additional electron must have come from somewhere else, right? So if this is the case, what we'll do is we'll keep 1 electron, which is from carbon originally, plus another electron which is from somewhere else. We write it as negative. And then we apply the second step once again. So for this time, we see that carbon has a total of 1, 2, 3, 4 negative charges. We do not count this, right? Because it's already from carbon itself. So for now, carbon will have a charge of, right, -4. Same thing for all these hydrogens, it's just like before, they have +1, +1, and +1. So these are the oxidation states of the atoms. So now the question is, how do we determine the charge on the carbon? Well, how do we determine it? What do you think? Now, this carbon has a charge of -4, while the adjacent hydrogens have a total of +3. So if you take -4 plus 3, you're going to get -1. You can either put a bracket over the whole thing and put a negative here, or sometimes what chemists do is that they allocate this negative charge to carbon, right? So either way works, and we can see from this example that this species has an overall charge of -1. Right? There is for this species, and in fact this species is known as a carboanion, right? Because it's obviously an anion since it's negatively charged. Right, next we can do the same thing for the next species, which is this, right? So same thing, first step, we allocate the minus plus, right? But this time we see that, hey, carbon only has 1, 2, 3 electrons around it. What this means is that, recall from just now that carbon has 4 electrons because it's from group 4. But for now, it only has 3 electrons. So what does it mean? It means that the additional electron must have been given away to something else, right? So now what this means is that this carbon now should have a positive charge because it has given 1 electron. So it will have a charge of positive, right? In replacement of that electron being lost. So then we apply the second step by circling it. So we count the oxygen state once again, and for carbon it will be -1, -2, -3, and then a +1, which will give it a charge of +2. -2, right? And for this hydrogen, it will be +1, +1, +1, right? So same thing, we can apply the same method to calculate the charge. So +1, +1, +1, -2 will give you a net charge of +1, right? And sometimes chemists do this by allocating the positive charge on carbon, right? So you have this species with a net charge of +1, and this is commonly known as a carbocation, right? Now compare this carbocation with this carbanion. The main difference between them is that for the carbanion, it is a negative charge, while for the carbocation, it is a positive charge, right? So next, I will not go through the other examples. You can work them out yourself. We will be talking about the next concept known as hybridization, right? Now, many schools do not teach hybridization, do not teach the reasons for hybridization. Instead, they just go into hybridization straight away. But I find it quite important to understand why there is a need for hybridization. So before you learn about the hows of hybridization, I'll teach you the why of hybridization, right? So this section already assumes you already know that how to describe the relative energy levels. So for example, you have an element, you should be able to tell me, right, how the electrons are arranged, and as well as sketch the respective atomic orbitals. So for example, for 2p orbitals, you should already know that, right, there are 3 orbitals along the x, y, and the z axis, and they have a shaded lobe, right? The shaded lobe simply represents a different phase of the orbital, right? Apart from this, you just have to know how to describe a covalent bond, which is the sharing of electrons. You should already know from this. You should already know this from your O levels, right? I believe. So now, let's look at why there is a need for hybridization. So why is hybridization necessary? Consider the following scenarios if you only use the very fundamental valence bond theory, right? Hybridization is actually another theory, right, compared to your valence bond theory. So if you look at the the molecule formed by carbon and hydrogen using only valence bond theory, you realize that there's actually one problem. Now, if we were to draw the energy levels of carbon, 2s, 2p, right? This is the energy level of the orbitals. You should know that carbon is from group 4, so you should have 4 electrons. So by your Aufbau principle and your Hund's rule, this is how the electrons should fill up, right? Now, you know that a covalent bond is formed by the sharing of 1 electron from either atom. So in order to form a covalent bond between carbon and hydrogen, what I'll need is hydrogen sharing 1 electron with carbon, right? But what problem do you see? Now for carbon, like what we drew just now, it only has 2 lone electrons, which means that if hydrogen were to bond with carbon, you should only 2 hydrogens should form a bond with carbon, right? For one of the hydrogen, its electron will share with this. For another hydrogen, its electron will share with this orbital, right? So what this means is that simply you will get a species with this structure, right? Since there's only 2 lone electrons to share with the hydrogen, and you should have another 2 electrons acting as the lone pair, right? Just take note that this bonding picture is the incorrect bonding picture, right? I'm now only teaching you why valence bond theory fails. So please don't describe methane or whatsoever in this way, right? This is the wrong way. I'm only using this to illustrate the need for hybridization, okay? So now, let's go back to this species. You should know that this species is rather unstable. Now, why is it unstable? You should already know from your O-levels something about octet rule, correct? Now, octet rule says that a species is the most stable if it has got 8 electrons around it. So if you were to count, for this carbon, there's only 6 electrons around it. So it's obviously not stable, right? Apart from that, if we were to write the molecular formula for this species, it has the molecular formula of CH2, which you know that is not stable because the most stable species between carbon and hydrogen is actually CH4. But how can CH4 form when carbon only has 1 and 2 lone electrons, right? There's not enough electrons to share to form 4 bonds with hydrogen. So it's actually not possible to form CH4 just by using the valence bond theory. Okay, so this is the first problem that you face, which I will call it the number of bonds problem from now on, right? Because it can't explain the number of bonds for CH4. So we call it the number of bonds problem. Now let's look at another case whereby we need to use hybridization instead of just valence bond theory. Now consider oxygen. Same thing, we start off by drawing the by sketching the energy level of the orbitals. So you know oxygen is from group 6, so you should have 6 electrons. 1, 2, 3, 4, 5, 6, right? Same thing, follow your Aufbau's principle, Hünzu, right? So now if you were to look at the species formed by oxygen and hydrogen, it should be quite obvious that this species is water, right? And you should be able to, by now, draw the structure of H2O, right? So this is the structure of H2O. Now, if we were to perform the same analysis as before, right, we should be able to deduce that in order to form a covalent bond, O need to have 2 lone electrons because there are 2 hydrogens, right? Well, it seems that there are in fact 2 lone electrons which can form 2 bonds with hydrogen. And it might seem that there's not really a need for hybridization, right? Because hey, this actually is perfectly fine, right? But if we look at the orbital orientations, the problem arises. Now recall that the p orbitals, right, x, y, z, are in this 3 orientation, the shadings, right? And if you were to combine these 2 pictures together, we'll see that one of the p orbital will have 2 electrons, one of the p orbital will have 1 electron, and another p orbital will have 1 electron, right? So in order to form a bond with hydrogen, the 1s orbital of hydrogen will approach in this way and do a head-on overlap with this py orbital. And another hydrogen will come and perform another head-on overlap with this p orbital to share the 2 electrons, right? So this hydrogen, and this p orbital is for oxygen, right? And of course, within this 2p, you have your 2s orbital, which is spherical in shape. Not draw it too elaborately, otherwise it will confuse you, right? So now let's focus on this diagram, right? If let's say we do not talk about any hybridization or whatsoever, and if we just use this bonding picture directly, what problem do you see? Now you have learned that the p orbitals are actually at right angles to each other, 90 degrees, right? Which means that if the two hydrogens were to approach the orbitals this way, the angle between them should also be 90 degrees. In other words, oxygen should be this shape, right? Because the bond angle is 90 degrees. Sorry, ignore the lone pair, right? Will be 90 degrees. Now, you should have learned that the lone pairs are situated like this, right? But what you have learned is that for water, although the lone pairs are situated like this, the bond angle is actually 107 degrees. So if we do not use valence bond theory, we will have a bond angle of 90 degrees. But in fact, water should have a bond angle of 107 degrees. So why is this happening? And we realized that if we were to use valence bond theory, we can't really explain why the bond angle is 107 degrees, because it should be 90, right? If we were to use valence bond theory. So this is the problem of valence bond theory once again. And just for a side note, right? If you were to look at the lone pair, right? These two lone pairs are definitely degenerate. In other words, they are similar. But if you were to look at the valence bond theory, right? One of the lone pair is situated in the p orbitals, another lone pair is situated in the s orbitals. We know that s is definitely lower in energy than your p orbitals, right? Which means that these two lone pairs are not degenerate, or you can say that they are of different energy levels. So if we were to use valence bond theory for water, we can see that there are mainly two problems, right? Just as a summary. First is the bond angle problem, and another is the positioning as well as energy of your lone pair, right? But obviously the bond angle problem is quite obviously observed for this case, right? So this is the reason for why valence bond theory failed. So just as a quick recap, you should be able to tell by now that there are two problems faced. One is the number of bonds problem. That's the first one, and the second one is the bond angle problem. So these are the two problems that you will face if we do not talk about valence bond, if we do not talk about hybridization theory. In other words, right, valence bond theory fails, right? Precisely because of these two observations. So now let's look at an example. Example 2, describe the problem that will be faced if valence bond theory is used to describe the structure of the molecule BH3, right? Same thing. Firstly, we start off with the energy levels. Now boron is from group 3, so you have 3 electrons. So we know that in order to form BH3, right, boron need to have 3 lone electrons, but for now there's only 1 lone electron. So by only using valence bond theory, we actually encounter the first problem, which is the number of bonds problem, right? Because we need to form 3, yet we can only form 1. So this is the problem that will be faced if we were to use valence bond theory for BH3, right? So now let's go into hybridization. In order to get rid of the problems faced, as well as a bunch of other problems which we don't have time to describe, the concept of hybridization was introduced. Hybridization is the mixing of orbitals to give a set of orbitals equivalent in energy to describe the inadequacy of valence bond theory. We will learn about the how of hybridization first before we come back to see how hybridization solved the problems faced previously, right? So before we go into detail, we need to keep in mind two basic rules of hybridization. First, the number of electrons before and after hybridization remains the same, and the number of orbitals before and after hybridization remains the same, right? So the two are always conserved. So let's look at sp3 hybridization. Just a side note, take note that hybridization do not really occur in a stepwise fashion. The following are simplified for your understanding, right? So please don't go and describe hybridization as a stepwise process, right? Because it's really just used to help you to understand it, right? So now for hybridization, there are mainly two steps. First step is the promotion of electron from 2s to empty 2p orbital, resulting in 4 singly occupied orbitals. So you can see from the diagram here, right, that one electron is promoted from the 2s to 2p. So now in total you should have 4 orbitals with a single electron, right? So that's the first step. Second step is the hybridization of one 2s orbital and 3 2p orbitals to give 4 equivalent sp3 hybrid orbitals, right? Now let's go back to the two rules of hybridization. The number of electrons before and after hybridization remains the same. So if you were to count the number of electrons before hybridization and after hybridization, right, you should see that, let me draw it out first, 1, 2, 3, 4. You should see that originally you have how many electrons? 1, 2, 3, 4, 5, 6 electrons, right? So after hybridization, you still have 6 electrons. The number of electrons are conserved. Now let's count the number of orbitals. So before hybridizing, you have 1, 2, 3, 4, 5. You have 5 orbitals. After hybridization, you still have 5 orbitals. It is also conserved, right? And one more thing to take note. For hybridization, we only hybridize these orbitals, and we didn't really touch the 1s orbital. So the 1s orbital will remain where it is at the same energy level. While for the other orbitals, right, since we hybridize them, the final energy level of them will be slightly lower than the 2p and slightly higher than your 2s. It makes sense, right? If you mix them together, it's going to get somewhere in between. So this is your sp3 hybridization. So how does sp3 hybridization solve the number of bonds and bond angle problem for CH4, which is your methane? Now, after hybridization, we have 4 of these orbitals, right? And these hybrid orbitals will arrange themselves in a tetrahedral geometry to minimize repulsion. So originally you have a s orbital and you have a p orbital, right? So after hybridization, what you're gonna get this lopsided, right? We call it the sp3 orbital. So you have 4 of this, right? So these orbitals will arrange themselves in a tetrahedral fashion, right? Just a recap, this is your tetrahedral shape. So one large lobe will be here. Remember, draw a small lobe, a small lobe, bigger lobe, small lobe, and another one which is behind, and a small lobe, right? So you're gonna have something like this, and look at the energy level, right? You have 1 electron in each of these orbitals. So you're gonna have 1 electron, 1 electron, 1 electron, and 1 electron. So in order to form a bond with hydrogen, right, each of these orbitals must overlap with 1 hydrogen. So the hydrogen will come here, 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 and lastly here, right? So now, is there a number of bonds problem? If let's say you are to analyze CH4, no, right? You have 4 bonds, and yes, it's well illustrated and well described using the hybridization theory. Now, is there a bond angle problem? You should know from your chemical bonding that for CH4, right, the bond angle is 109.5. Remember what I said just now? These 4 hybrid orbitals will arrange themselves in a tetrahedral geometry to minimize repulsion. This is exactly your VSEPR theory. And in order to minimize repulsion, the bond angle will be 109.5 degrees as well. So this theory, hybridization theory, actually describes your geometry as well as your number of bonds very well. So that's why hybridization should be used instead of valence bond theory for structures, right? So this is for your sp3. And if you were to look at ethane, let's just use this diagram, right? Now if you were to look at ethane, what happens in ethane is that each carbon is sp3 hybridized, like what we described here, right? So 3 of the sp3 orbitals overlap with the 1s orbitals of the hydrogen, while the 4th overlaps with the sp3 orbital of another carbon. So these two overlap will form a sigma bond, and the overlap with the 1s orbitals of hydrogen forms another 3 sigma bonds, right? So this is the structure of your ethane. We have come to the end of our trial lesson. So if you are interested, please contact me via my email or my contact number. Thank you.